Okay, this video is over the perpendicular bisector theorem, and we're going to start this video out a little bit differently. Normally I start on the front of the page, but we're actually going to do an activity prior to doing this video. So what I'd like for you to do is I'd like for you to go get a ruler, and you're going to use that ruler for this page. Pause the video if you don't have it, and go get you a ruler right now, please. Alright, so we're coming back. I've got my ruler, y'all have got your ruler, and we're going to move on. So what you're going to do, fold your paper in half just like we always do. It's not going to be even on the front. Please don't worry about that. It's not that big of a deal that it's not even. We really need it to be exactly in half for the back side, for what we're going to do on the inside. Take your pencil, and along the bottom, I want you to mark this side with a dot and call it point A. I'd also like for you to mark a dot on the crease and call this point C. And then we're going to mark a dot over here, and we're going to call this point B. Okay? Alright, so currently what we have is, what is this thing called that cuts this into two equal segments? Do you remember the vocabulary from last time? Currently it's called a bisector. Now, specifically, this one is called a perpendicular bisector, and that is because I know the angle down here is a right angle. Okay? So we call this line a perpendicular bisector because it makes a right angle. And it separates into two equal or congruent parts. Okay? Perpendicular bisector because it's a right angle and it separates into two congruent parts. That's the definition. So, what we're going to notice is a pattern of things, okay, that happen with this. So, go ahead and pause the video if you didn't get all that copied down yet. If you did, let's move on. I'm going to zoom out again. What I want you to do is I want you to pick 3 points on this line and put a dot anywhere you want. So I'm going to put a dot here, I'm going to put a dot here, and I'm going to put a dot way down here. Okay? And we're going to label these points D, E, and F. Now, your points don't have to be spread out like mine. Wherever you put them, everybody's is different, and that's supposed to kind of show how no matter what you do, it's going to be this result. Okay? So my numbers are going to be different than yours, and that's okay. Alright? Now, what I want you to do is I want you to notice something that happens. Okay? If I connect D to B, okay? So I'm going to take my ruler, and I'm going to draw a line that connects point D to point B. Okay? I'm also going to measure this line. I'm going to measure in centimeters just because centimeters are easier to measure in, and I get 20 centimeters. Okay? So, connect the line and then measure it in centimeters. Remember, centimeters are the smaller side of your ruler. The other side is inches. Do the same thing on the other side. Connect D to A. And while you're at it, go ahead and measure how long it is from D to A. Mine measures 20 centimeters. Okay? That's interesting. So this cuts the line in half, and it's a perpendicular bisector. And look at that. Those two sides are congruent. Alright, let's do the same thing with point E. We're going to connect point E to point B, and we're going to measure it. From E to B is 17 centimeters. Don't worry about the decimals. Just call it a whole number if you can. And now we're going to connect point A to point E, and we're going to measure it. And that also is 17 centimeters. So when I connected this point to B and this point to A, which is a point on the perpendicular bisector, I notice so far that no matter where I've connected it, the lines that connect them are the same length. Look at that. So what do you think is going to happen with F? Well, the lines should end up being the same length. Let's try it. So from F to B, I got 15 centimeters. And from F to A, I also got 15 centimeters. Okay. So, it worked out. No matter where I am on the line, I could even take my ruler and measure, like maybe put another dot on there and say, okay, this one is 16, and then from here to here, let me check it just to see. Oh, look, that one's also 16. Okay, so anywhere on this line, if I'm on the perpendicular bisector, then that means I'm going to be equidistant from the endpoints of the original line. This is my original line down here at the bottom. Okay, so we're going to use that to answer a few questions. This is called the perpendicular bisector theorem. It says a point is on the perpendicular bisector, and we can actually fold it this way now if we want to just kind of see it better. Okay, so it says if a point is on the perpendicular bisector, this means perpendicular bisector, okay? So that's just the abbreviation we use in geometry. Then it is equidistant, meaning equal distance, from the endpoints, okay? So, note, the perpendicular bisector does not have to go through the vertex of a triangle, okay? So this is some different ways that we're going to see it. So this is a perpendicular bisector because it bisects the segment CD, but it doesn't go through E. This is a perpendicular bisector because it bisects ML at a perpendicular angle or right angle, but it doesn't go through the vertex. The ones we're going to look at today are the ones where it goes through the vertex at the top. Okay, so this is OQ, and that's a perpendicular bisector because it's a right angle. So what does that mean? Well, that means that this point right here is on the perpendicular bisector, so this segment is going to be congruent to this segment. Okay, so these are the ones we're going to look at today. These are the examples. This is what they're going to look like today. Okay, so let's look at example 1. It says that this is a perpendicular bisector. It says find x. Well, that segment's going to be equal to that segment. 7x plus 10 equals 9x minus 2. So we're going to solve. Subtract 7x from both sides. That says 2. Okay. So this is 10 equals 2x minus 2. Add 2 to both sides. 12 equals 2x. Divide by 2. X equals 6. So x equals 6. Then it asks for the length of AD. Well, this is just what we did on the last worksheet, right? So what's the length of AD? Well, if I find from A to B, then I can multiply that by 2 to get the whole length, right? So 7, what's x? It's 6. So 7 times 6 plus 10, that's 42 plus 10, so 52. Multiply that by 2, and so it's 52 times 2, which is 104. So AD is 104. Okay. Alright, another example. What is QR? Well, QR is this length right here, and this is a perpendicular bisector, and that's because I know that these are the same lengths. So what does that mean? Well, that means that point Q, since it's on the perpendicular bisector, is equidistant from here to P as it is from here to R. So that means 3n minus 1 equals 5n minus 7. Solve. Subtract 3n from both sides. Negative 1 equals 2n minus 7. Add 7. 6 equals 2n. Divide by 2. N equals 3. Is that what they asked for? No, they asked for the length of QR. So let's plug it in. What is n? N is 3, so 5 times 3 minus 7. 15 minus 7, that's 8. So QR equals 8. Okay? Stuff is easy, right? Alright, moving on to the inside. Oh, we're done. Woohoo! Forgot. We don't have any more examples over this. So really and truly, it's just if you have a perpendicular bisector, that means the segments down here are equal and the sides are equal. It's an isosceles triangle. Alright, thanks so much. We're going to glue this in on the next page of our notes, which is on page 30. 39 of your spiral. Thanks so much for watching.